Um, my topic of presentation will be complexity in complex fluid flows. Um, so the outline of my presentation will be like uh, first I will talk about briefly about complex fluids. Then I will try to show you some of the simplest constitutive models that people use for complex fluids, and then I will discuss one of the key aspects that we should know if we want to study the flow dynamics of complex fluids, which is the time scale of observations. And then I will tell you some real world examples in terms of experiments from where actually you can see some of the well-known non-linear behavior of complex fluids. Then I will come to one of the widely investigated phenomena that actually these days people are doing in the area of complex fluids, which is elastic instability and elastic turbulence. That I will shed some light on that and their applications. And at the end of my talk, I'll particularly focus on a topic which will be flow of complex fluids, particularly viscoelastic fluids, um, through microporous media. Then I will conclude my presentations. Okay, so my presentation will be divided into two parts. In the first part, actually, I'll try to give the overview about the complex fluids, their interesting and peculiar behaviors. Those are associated with complex fluid. So that I will explain, and I will try to show some of those. And in the second part of my talk, I'll keep my focus on a particular topic, which is the flow of complex fluid through microporous media. Okay, so first thing first, what are complex fluids? So uh, so I think we have been studying this, from our BTech days. Okay, where in undergrad fluid mechanics we used to come across um, with this very well known schematic where we have two parallel plates. The lower plate is fixed, whereas the upper plate is moving with some velocity v due to application of some forces F. Okay, now in between these two plates we have kept some fluid, simple Newtonian fluid. Okay, now the force that we are applying per unit area, which is simply stress, in this case will be proportional to du by dy, which is the velocity gradient. Okay, now if we want to equate these two, so then we need a coefficient which is called viscosity of the liquid. Okay, so now you can see that there is a linear relationship present between this tau and dy by dy, and mu being the uh, constant of coefficient. Okay, so when there is a linear relationship between this tau and dy is present, so then we simply call that fluid as simple Newtonian fluid. But when the linear relationship between this tau and dy and dy by dy becomes non-linear in nature, then we simply call that as a non-Newtonian or complex fluids. So it is as simple as it is. Okay, but the question is that how we can determine this, the relationship between these tau and dy whether it is linear or non-linear. So how we can do that? And in order to do that, what do? You use one instrument which is called rheometer, where we have different techniques, different setups by which actually you can determine whether the relationship between tau and duv by dy will be linear or non-linear. And and this domain of research is called rheology, and the technique that you utilize to establish the relationship, it's called rheometry, and the instrument that we use, it's called rheometer. Okay, so from this slide what we can learn is that whenever there is a non-linear relationship present between tau and du by dy for this simple flow setup, then we can simply call that fluid as non-Newtonian or complex fluid. Okay, now so if you want to ask me a formal definition of complex fluid, so this is the definition that I have taken from Wikipedia. Okay, so complex fluids are generally mixture of, generally mixtures that have a coexistence between two phases, like solid liquid. For instance, you can have a solvent like water, and you can put some solid polymers into it, which will become polymer solution. That is a kind of well-known complex fluid. Similarly, you can have solid gas, which is like granular mixture or flow, solid liquid gas forms, so liquid emulsions. So all these are subclasses of complex fluids. Okay, now most of the complex fluids exhibit, you know, one very well-known non-Newtonian behavior, which is called viscoelastic behavior. So we have two extreme cases of behaviors of, of material like viscous fluid, which that I just explained in the earlier slide, is Newtonian fluids obeys the Newton's law of viscosity. Okay, and we have another extreme which is called elastic solid, and we all know that for elastic solid we have that well-known Hooke's law of elastic solid. Okay, but interestingly, viscoelastic actually fluids, which most of the complex fluid exhibit, contain both this viscous behavior as well as elastic behavior. Okay, so that's why they are called viscoelastic behaviors. And interestingly, most of the fluids that we use in our daily life, like shampoo, paint, paste, gel, all actually fall into this category of viscoelastic fluids. So definitely we need to understand these fluids thoroughly, in order to study their flow behavior. And to do that, first of all, what do we need? We need a constitutive model. For instance, for viscous fluid we have Newton's law of viscosity. Similarly, for elastic solid we have Hooke's law of elastic solid. So all these are constitutive models. Okay, similarly for viscoelastic fluids we have a very well-known constitutive model which is called Maxwell model. Okay, so this is the simplest viscoelastic constitutive model that we have till day. Okay, it's very simple, and still it is, despite having a lot of constitutive models, this is the model that people still use. Okay, in very often. Okay, in order to study the flow dynamics of viscoelastic fluids, and this model was proposed by James Clerk Maxwell. Okay, uh, this gentleman is the same Maxwell who proposed a lot of laws for electromagnetism. Okay, and you will be surprised to know that he proposed this law for gases. So it was like related to kinetic theory of gases, and then later people realized that this model could be also utilized for viscoelastic fluids. So the basic concept of this model is that it consists of two, you know um, two kind of scenarios, okay, which are connected in series. One is dashpot, which will dictate the viscous response of the viscoelastic fluid, and we have one spring which will dictate the elastic response of the viscoelastic fluid. Now if we combine these two in series, then you will have a very simple constitutive model for viscoelastic fluid. So you can do some mathematical analysis, and then you can come up with this simple viscoelastic constitutive model. But the interesting thing is that in this model we have a parameter which is called lambda, generally designated as lambda, which is nothing but material relaxation time. So this lambda says about, so when you apply some force on a fluid, so there will be some deformation within the fluid. So lambda will tell you that how long that fluid will take to adjust that deformation. Okay, and you can easily determine this value experimentally. There are many techniques available in the literature by which you can actually determine the value of lambda. Okay, so this is one time scale that is very important if you want to study the flow dynamics of viscoelastic fluid. Then the question is that how we can quantify the fluid viscosity. So there should be something that we can utilize to say that this fluid is very like very elastic or very viscous, or It has both viscous as well as elastic behavior. And to do that, Professor Reiner, who is one of the well-known rheologists, who proposed one non-dimensional number which is called Deborah number, which is designated as d is equal to Tc by Tp. So Tc is the time that a material takes to adjust to apply stress of deformations. It is the same lambda that I discussed in the last slide. Okay, and Tp is the time scale of observations. Okay, so okay, according to Professor Reiner, when this Deborah number is much smaller than 1, then the material will behave like a fluid. Okay, and when the Deborah number will become much larger than 1, then the fluid then the material will behave like a solid. Okay, now, so in order to explain it, he actually he actually proposed a very famous quote, and I'll just read this quote and then I'll try to explain what actually it says. So according to him, so Deborah knew two things. First, that the mountains flow as everything flows, but secondly, that they flowed before the Lord and not before man, for the simple reason that man in his short lifetime cannot see them flowing, while the time of observation of God is infinite. We may therefore well define a non-dimensional number, the Deborah number. So basically, what he was trying to say that, so Deborah actually was a prophet in Bible. Okay, so according to Professor Reiner, that God actually has a infinite time scale of observation. Okay, so according to God, you know, everything is flowing, even the mountain is also flowing. So according to God, everything is like a fluid. Okay, because the time scale of observation is infinite, so definitely the Deborah number will be much smaller than 1. But in case of human being, so our time scale of observation will be definitely much smaller. Okay, maybe 100 years or maybe 70 years in that scale. And within that scale of time of observation, so definitely we will not able to see that mountain is flowing. Okay, so for us mountain will be like a solid. Okay, because then Deborah number will be definitely larger than 1. Okay, because this Tp becomes definitely smaller for a human being. So that was the code that he wrote to explain the significance of this Deborah number. Okay, now I'll give you some simple examples by which you'll be able to understand more the significance of this time scale of observations. So to do that, what I'll do, I'll just give you an example of putty, which is widely used for building construction. Okay, so you can take putty and then you can make out a ball out of that putty, and then you can simply drop it on a plain surface and you will be able to see that the ball actually is bouncing back. Okay, so here actually the time scale of observations or the time scale of experiment will be very small, maybe 2-3 seconds, and within the time scale of observations you can see it behaves like a solid. But you can place that same putty on a plane which has a hole and keep it for maybe 2-3 days or 10 days, and then you will see that the putty actually is flowing. Okay, so if your time scale of observation is like 2 to 3 days or even 10 days and larger than that, then you can see that the same material is behaving like a fluid. Okay, so the time scale of observation is definitely important. Okay, so that is the concept that Professor Reiner proposed. Okay, and then there is an interesting experiment that is still going on. Okay, at the University of Queensland, Australia, where actually people took a material which is pitch that is used for road construction. So what they did, they put that material on in a funnel, and then they started the experiments almost 100 years back, 1927. And what they observed, that after 10 years one drop of pitch actually came out from the nozzle. Okay, so and then the last drop that came out from the nozzle was at 2014. Okay, so if your time scale observation is this, like over 100 years almost, then the putty, which looks like solid to us, unless you heat it up and make it liquid, the putty will is like a it behaves like a fluid. Okay, and this experiment is still going on at University of Queensland. And if you search in Google, just by typing this name, pitch drop experiment, you will still able to see, because there is live demonstration still going on. Okay. uh, so yeah, so the main thing is that the time scale of observation is very important. Okay, when you want to designate a material, whether it is fluid or solid, or both, it has both, solid and fluidic behavior, so that is very important. Okay, so now, uh, so complex fluid exhibit different nonlinear behaviors, as I told in the introductory slide. Okay, and one of those nonlinear behavior is the shear thinning or pseudoplastic behavior. So shear thinning is nothing but, if you increase your rate of deformations within the material, so what will happen, the viscosity will keep decreasing. Okay, so this is the shear thinning behavior. For neutral fluid, the viscosity will remain constant. Okay, it will not depend on the rate of deformations. For instance, here it is shear rate, and in case of shear thickening fluid, an exactly opposite trend will happen, where the viscosity will increase as we increase the shear rate. Okay, now if you see at the molecular level, okay, what is happening, okay, why this shear thinning behavior or shear thickening behavior actually occurs. So for instance, you can take the simple example of polymer solutions, where you have solvent and you have polymer molecules present in it. Okay, now when you apply some deformations or some force with to this solutions, then what will happen, the molecules those are present inside the polymer solutions, they will be stretched, they will be aligned. Okay, and as a result, what will happen, the viscosity also will be definitely prone to change. Okay, because viscosity is nothing but the resistance in the flow. And then when this conformation changes in the molecule will happen, so definitely the resistance also will change, and as a result the viscosity of the solution will also change. Okay, similarly for other like cases like suspensions, where you have needle like particles, those will be also arranged in a particular manner under deformations. Similarly, you can say emulsions also. So all this rearrangement of the fluid microstructure that is present within the fluid will the rearrangement will happen, and as a result the viscosity also will tend to change. Okay, so this is like a simple one experiment that AOL research group has done. So this is like a shear thinning fluid, and this is a simple fluid. You can see that the shear thinning fluid easily come out from the syringe, because you are applying some force, the viscosity will decrease. As a result, it will come out from the syringe. But once it comes out from the syringe, now if you tilt the surface, that simple fluid actually flows down, but the shear thin fluid is not flowing down, because now there is no force except the weight of the liquid. um, and then viscosity again increases because there is no force, and except the definitely body like weight of the fluid, so that's why it's not flowing down. Okay, and then people actually have done sophisticated experiments, and also observe those molecular changes that I was talking about. This is like a fluorescent level polymer molecules, and you can see how it is changing its shape and conformations under under an applied force. Okay, so I can give you a lot of examples about shear thinning or pseudoplastic behaviors. One of the best example that I can give is paint. Okay, so paint actually also exhibits shear thinning behavior. Okay, so when paint is at rest in a bucket, so the viscosity will be higher. Okay, but once you try to push a brush inside the paint, so then what is happening, you are applying some force, so the rate of deformation actually increases, so the viscosity will decrease, and that's why the brush will easily go into the paint. And then when you rub it on the wall, again you are applying force, again the viscosity will decrease, so it will easily, you can easily rub on the plane on the surface of the wall. And once you remove the brush, then what will happen, there is no force, so paint definitely will stick to the wall, because the viscosity again will increase. Okay, in these winter days, we always apply some moisturizer cream on our skin, which is also a perfect example of shear thinning fluid. Okay, because when you rub the cream on your skin, so definitely you are applying some force. As a result, the viscosity will decrease, and the cream will be spreaded very nicely on your skin because the viscosity will be decreased. Even our blood that is flowing within our body, so that also exhibits shear thinning behavior. Okay, similarly, I can give you many examples for shear thickening fluids. Okay, and then shear thickening behavior again will arise due to the rearrangement of the fluid microstructure that will present. Like here, actually, due to the formation of clustering of particles. Okay, this shear thickening behavior can be originated, and the best example I can give you is the quicksand. Okay, so you might have experienced that if you fall in a quicksand, now if you try to come out from that quicksand very quickly, so definitely you will not be able to do that. Okay, because when you are trying to push your leg maybe very quickly, then you are applying a lot of force, and as a result, what will happen, the viscosity of the surrounding fluid definitely will increase, and that's why you will not be able to come out. But if you do it very gently or slowly, so definitely you will be able to do, if you definitely you will be able to come out from the quicksand. And by actually considering this behavior of shearing fluids, people actually doing a lot of research to make armor, liquid armor, to stop bullets, because when a bullet will hit a jacket which is made out of shear thickening fluids, then what will happen, the viscosity will be drastically increased, which will actually stop the bullet in stop the bullet, and it will not allow to pass through. Okay, so that's why a lot of research is happening and how to utilize these shear thickening fluids to make liquid armor. Okay, now apart from this, I'll talk about another interesting nonlinear behavior that actually most of the complex fluids exhibit, which is the presence of normal stresses. So this is the same flow setup that I talked in the last slide. Two parallel plates. If you keep a simple fluid, Newtonian fluid, so definitely it will originate a stress component in the flow directions. But if you keep a complex fluid or viscoelastic fluid, then what will happen, along with the stress component in the flow directions, it will also generate some stress component normal to the flow directions, which are called normal stress. These are generally measured in terms of normal stress difference. Okay, N1 and N2. N1 is the first normal stress difference, and N2 is the second normal stress difference, or in terms of normal stress coefficient, psi 1 and psi 2. Okay, so so because of the presence of this non-linear elastic normal stresses, this complex fluid, particularly viscoelastic fluids, exhibit uh, very interesting and complex flow behaviors that I am going to show some of them. Okay, and the first example that I am going to give you is the rod climbing or Ojama number effect. Okay, this is very famous example that we always give. Okay, so in this experiment we have two fluids, one is Newtonian and one is non-Newtonian viscoelastic fluids. Now if you start this fluid, what will happen, in case of Newtonian fluid, the fluid will be thrown towards the wall of the beaker. But in case of non-Newtonian viscoelastic fluid, what will happen, the fluid actually will try to climb along the rod of the star. Okay, so exact opposite that will happen compared to the Newtonian fluid, and this is happening purely due to the presence of this elastic normal stresses. Okay, and another example that I can give you is the this dye soil effect or extrude soil effect. Okay, here again we are pushing two fluids, one is Newtonian and another is complex viscoelastic fluid. Okay, through these two syringes. In case of viscoelastic fluid, you can see that the fluid that is coming out from the syringe is kind of soiled up, but in case of Newtonian fluid, it's like it doesn't soil. Okay, and why it is happening, because when the fluid is going through this syringe, So it will experience a lot of kind of definitely force, and as a result those fluid microstructure that will be present within the fluid, that will be stretched, elongated, okay, when they will travel through the syringe. But once they come out from the syringe, they will try to definitely release themselves, okay. They will try to go to their initial kind of equilibrium configurations. So as a result the fluid will be swelled up, okay. So this is famously called die-swell effect or extrude-swell effect, and again it is happening purely due to the presence of these normal elastic stresses which are associated with the viscoelastic fluids. Okay, now I can give you many other examples. Okay, this interesting and complex flow behavior of viscoelastic fluid. This is like the extensional thickening behavior. Okay, so here, uh, as I am keep telling you that those fluid microstructure like polymer molecules, okay, will be stretched and aligned, and because of those, elastic normal stresses will be generated, and also uh, those interesting complex flow behavior can be observed. So this is like one example which is called open siphon effect, where this gentleman is trying to get in the liquid into the syringe, and you can see that although the syringe doesn't touch the liquid surface, but still the liquid is going into the syringe, okay. So, and this is purely happening because of this extensional thickening behavior that is occurring within the viscoelastic fluids. Similarly,
Looks
you
good.
can
Yeah,
see
it looked like it was working.
in this example, the fluid is going out from the beaker.
This is
Wow, that one was
Purely
really
because
good.
of
this
this
is yeah.
extension
This
Similarly,
one
in
is
these
cool.
examples,
Good
with a
stuff, man.
simple neutron fluid, nothing will happen. But in case of this plastic fluid, you can see that this kind of sheet will be formed purely due to this extensional thickening behavior. Okay. So now I'll talk about another interesting and complex phenomena that very often seen uh, during the flow of complex fluid, which is called elastic turbulence. Okay, so we have already you know we have studied like about hydrodynamic turbulence at different stages of our you know kind of studies, okay, maybe in BTech and MTech or even PhD. And then and then that hydrodynamic turbulence is dictated by this famous non-dimensional number, which is the Reynolds number, which you all know that it is the ratio of inertial forces to that of viscous forces. And this is the perfect example that we always give to explain the hydrodynamic turbulence. So we all know that when the Reynolds number will is lesser than 2300, and then the flow will be laminar, it will be smooth, okay, and ordered. But when this Reynolds number gradually increase, the flow will be also gradually will transit to more chaotic and fluctuating state. For instance, when the Reynolds number will become larger than 4000, you can have this turbulent flow, okay. Even if you plot the velocity field at a probe location inside this flow in a pipe system, you will see in case of laminar the flow field will be very smooth, ordered. But as we keep increasing the Reynolds number, it will be ultimately chaotic and fluctuating uh, you know behavior that we can have due to this turbulent flow, okay. So this is well known, okay. So this we have already studied, okay, many times. And this transitional flow from laminar to turbulence occurs definitely due to the inertial forces. So this transition in the flow is dictated by by the inertial forces that will be present within the fluid, okay. But now what will happen if the system, okay, the system size becomes much smaller, like in millimeter scale or even micro scale, which we generally see in case of microfluidic systems. Then the Reynolds number will be definitely much smaller than 1, because your d becomes smaller, okay. So the chance of getting hydrodynamic turbulence in a microfluidic system will be very lesser, okay. But interestingly, you can take the same solvent like water. Now if you add a little bit polymer, even in ppm quantity, okay, and then we flow the same solutions as that polymer solution through a microfluidic geometry. Just like here, actually, it's like a simple channel which is in millimeter scale, and we have some obstacles inside it. And interestingly, you can see that the flow field also will become chaotic and fluctuating in nature, just like regular hydrodynamic turbulence. Okay, so here, although we have negligible inertia because our Reynolds number is very small, but still we can have this chaotic and fluctuating flow behavior, just like hydrodynamic turbulence. Okay, so this is called elastic turbulence. So here, inertial forces definitely not the dominating, or the driving force for turbulence, but here elastic normal stresses that I discussed, few slides back. So those actually are the driving forces to generate this turbulence, and that's why it's called elastic turbulence. And these days, actually, a lot of people are working on this topic. Okay, because because it has huge potential in microfluidic system, because in microfluidic systems, so flow will be mostly laminar unless we apply some external force like electric field or magnetic field. It will be mostly laminar, and there actually it will be very hard to, in laminar flow it will be very hard to increase the rates of transport processes like mixing or heat transfer. Okay, or some chemical reactions, if you want to, increase the rate of chemical reaction, so it will be very hard to do because the flows will be laminar. Okay, but somehow if you can induce elastic turbulence within that microfluidic system, so definitely it will help you to increase the rate of those transport processes. And that actually, uh, you know that's why a lot of people are working on this topic these days. Okay, now, so definitely, uh, the flow will definitely not directly go to the elastic turbulence regime. So before going to that regime, so there will be an instability that will be generated within the system, which is called elastic instability. And that actually, again, is related to that normal elastic stresses that I talked about. Okay, so in order to understand how this elastic instability, can be generated, so I have given a kind of very simple example. Like, suppose you imagine like there is a flow of complex viscoelastic fluid that is happening through a curvilinear geometry. Okay, and where we have a velocity field. Now imagine within the viscoelastic fluid we have those fluid microstructure or polymer molecules. Now if you place a polymer molecule inside this velocity field, then what will happen? There will be unequal stretching in the polymer molecule because of this velocity gradient. And as long as there is an unequal stretching of polymer molecules, so there will be some stresses, that will be generated, which is nothing but our elastic stresses, which is also called hoop stress. Okay, now now this uh, stress actually is again now coupled to the momentum equations. Okay, which also determine the pressure field. Okay, now because of this coupling between the stress and momentum equation and pressure field, what will happen? There will be a generation in the velocity field along the radial directions. So if there is a generation of velocity field in the radial directions, to obey the mass conservation principle, so there will be also a velocity field, that will be generated in the axial directions. So there will be kind of amplification of perturbation that will happen as a result. So that's why ultimately we will have an instability that will be generated within this system. Okay, but if you increase the flow strength or material relaxation time, then ultimately that elastic instability will be transiting to that elastic turbulence regime. So elastic instability is the triggering point of elastic turbulence. Okay, so that's why people are doing a lot of studies in terms of theoretical, numerical, even experiment, in terms of experiments, to also understand this elastic instability phenomena, and which is very common for the flow of complex viscoelastic fluids. Okay, so in our group also we have done, we are doing a lot of research in this directions. Okay, we have also shown that how we can utilize this elastic turbulence to increase the rate of heat transfer. So for instance, in this example we have taken a very simple flow setup which is called lead driven cavity, and we fill this lid driven cavity with a viscoelastic fluid. And then what we have seen that if you increase the Auger number, which actually dictates your the extent of fluid viscosity. So as you increase the Auger number, so the extent of fluid viscosity will also increase. You can see that once it exceeds a critical value, the heat transfer rate will be drastically increased. Okay, which is here defined by this Nusselt number. Okay, which is nothing but non-dimensional heat transfer rate. So you can see that it can be increased by more than 100%. Okay, by inducing this elastic turbulence within this system. Okay, so even other research group also, they perform experiments and they also observe this kind of drastic increase in heat transfer rate due to the presence of this turbulence phenomena. Okay, other group, they also perform experiments and they have also seen this kind of increase, drastic increase in the heat transfer rate. Okay, so not only heat transfer rate, we will have even have seen like that if we can induce elastic turbulence, it can also facilitate the mixing of fluids. For instance, in this seminal experimental work by Professor Stanberg from Weizen Institute, what they observed that if you place a dye, okay, in a flow system like this, if the fluid is simple water, then you can see that even after 9 hours the dye will be dispersed like this, mainly because of diffusion. But if you use instead of water plus polymer, then you can see that uh, after 8 minutes how the dye will be quickly mixed inside this flow system, and that is purely because of the origin of this elastic turbulence within the system. Okay, and even in our research group also we performed numerical simulation, and we have shown that how we can leverage this elastic turbulence and you can easily mix two fluids in a curvilinear microchannel. So this is for Newtonian, simple Newtonian fluid. Okay, and this is for viscoelastic fluid, and how you can see that how the two fluids can be mixed very easily in a curvilinear microchannel by inducing this elastic turbulence. Okay, so definitely this elastic turbulence phenomena has a lot of potential, you know um, for particularly microfluidic systems, if you want to increase the rates of transport processes like heat transfer and mixing. Okay, now actually I'll talk about on a particular topic, which is like flow of viscoelastic fluids through microporous media. So this problem actually has a lot of practical applications. For instance, in enhanced oil recovery, where people generally take water and then add some polymers into it, and then they inject that polymer solutions into the oil reservoir to get out those trapped oil from the porous rock. Okay, so this is a perfect example where actually you can observe the flow of viscoelastic fluid through a microporous media. Similarly, in packed bed reactor also, if you have a reactor and which is filled with catalyst particles, and if you are dealing with some complex fluids, so now if you want to control the reaction rate within this packed bed reactor, so definitely you need to thoroughly understand the flow dynamics that is happening within this porous system. Okay, some other application like soil remediation filtration also, we can see this flow of complex fluids through microporous media. So this is kind of motivation why actually we have been studying this topic from the past 2-3 years. Okay, so now interestingly, when complex fluid like viscoelastic fluid flows through these microporous media, these two peculiar behavior that people and even we also observed. One is formation of preferential paths or lanes, another is non-monitoring variation, velocity fluctuation and pressure drop. So I'll go one by one and try to explain what do they mean and how, and we have proposed some mechanism for the occurrence of these two peculiar behaviors. Okay, so first I'll go with this formation of preferential paths or lanes. Okay, so in order to understand that, I'll give you the experiment that has been done by Muller et al. Almost 30 years back. So what they did, they actually took a model porous media, like they have taken a glass pipe, and they have kept some glass spheres within that glass pipe. So it, you can think it's like a model porous media. Okay, now they flowed two solutions within this through this model porous media. One is only solvent, which is paraffin oil, and another is paraffin oil plus some polymers. Okay, now in case of only solvent, which is paraffin oil, what they observe experimentally is that the fluid is passing through all the paths those are available within the this model porous system. Okay, but in case of viscoelastic solution, polymer solutions, you can see there are certain paths where most of the fluids passing through and completely avoiding other paths those are available. So this is at one time instance, but at next time instance this path actually is shifted to another place. You can see this is the place at this time instant, and again in next at next time instance this path actually shifted back to its original positions. So some preferential paths or lanes are forming, those are even not fixed, those are also changing their position with time. So these people actually first term this phenomenon as a preferential path or lanes that is forming during the flow of viscoelastic fluid through microporous media. Okay, now in order to understand this this flow behavior, very recently Professor Emerson group from Okinawa Institute of Science and Technology, they did a much simpler experiment where actually they took one microchannel and then they kept two micropillars inside it. Okay, and and they flowed a surfactant solution which is also viscoelastic in nature through this setup. Okay, and they also had the gap between the two micropillars, which is defined by this gap ratio G. Now when the gap ratio is 0.5, you can see that at very low flow strength, which is defined by this dimensional number which is called Weisbach number, the fluid is passing through all the paths those are available. Okay, but as they gradually increase the flow strength, you can see that in this case the fluid is passing through these two paths those are available and completely avoiding this path, which is actually the termed as diverging state or D state. Okay, when they increase the flow rate further, then what they have seen that the fluid is passing now through this path only and completely avoiding this path and this path. So this is the termed as asymmetric diverging state or eddy state. Okay, now when they increase the gap ratio a little bit, 0.603, then you can see that at low flow strength again the fluid is passing through all the paths those are available, but when they increase the flow strength a little bit, and you can see that now the fluid is passing mainly through this path that is available between the two micropillars. So this is the term as converging state. So 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 then they propose that this could be the starting point for the formation of those preferential paths that actually Muller et al. Actually observed, through that three-dimensional model porous media. Okay, so then what we did, we also performed numerical simulations with almost the same setup that Professor Emerson group used in their experiments, and we have also seen the same kind of formation of diverging state for this gap ratio, and then asymmetric diverging state for this gap ratio as we keep increasing the YO number. In case of a little bit higher gap ratio, what we have seen that the formation of that same converging state or C state. Okay, now these are the video actually where you can clearly observe the formation of those different flow states. So this is the diverging state, this is the asymmetric diverging state, and this is the converging state. Okay, but the question remains like same, like why does this happen, why this flow transition happens. Okay, so that we need to understand. Okay, so in order to understand that, what we did, so we actually look into this look into this formation of birefringent strands. So what is birefringent strand? So if you take a simple like if you take a simple system like flow in a microchannel where you have only one obstacle, then what will happen? If you flow a viscoelastic complex fluid, then what will happen? At the downstream of this micropillar, those fluid microstructures like polymer molecules will be stretched and they will be aligned, and as a result one strand will be formed, which is called birefringent strand. Okay, and as you keep increasing the flow strength, then what will happen? Those strands will be larger in size, their width also will be increased. Okay, so these are the strands which are the zones of high elastic stresses. Okay, and uh, they could be the region to guide the formation of those defined flow states. So that's why what we did, we calculated this birefringent strand for our case. For instance, this is the case of diverging state. Okay, here you can see that those strands will be formed, but they also will be combined together and form a single strand. Now now you can imagine that if fluid now wants to travel through this path, so definitely the strands will not allow it to flow through this path. So that's why the fluid will flow only through these two paths, those are available. So this is nothing but the diverging state. Now when this strands actually, as you keep increase the flow strength, what will happen? The width and as well as length, the strength of these strands also will be increased. That's why they will start fluctuating, because of those elastic instability. Now you can imagine at once time instance this strand actually goes down, so definitely now it will not allow the fluid to flow through this region as well as this region, and now it will only, the fluid will be only allowed to flow through this region, which is nothing but our asymmetric diverging state. Okay, now if you increase the gap ratio a little bit, zero point 0.5, then what will happen? These strands actually now not be allowed to combine together. Now there is a space between the two micropillars. Now the fluid will be able to flow through this region. So this is nothing but our converging state. So in terms of, so definitely now we can easily observe that these birefringent strands that will be formed, okay, those will be the guiding or the driving force behind the formation of those, of different flow states, and or the formation of those different preferential paths, during the flow of viscoelastic fluid through microporous media. So that we explained in our study. Okay, so this is the overall mechanism that I just explained. Okay, now, so yeah, so now the peculiar behavior I explained. Now come to the next one: non-monotonic variation in velocity fluctuations and pressure drop. So in this case, what will happen? So to understand what is non-monotonic variations in velocity fluctuation and pressure drop, so again, a very famous group who is doing a lot of research on flow of viscoelastic fluids through microporous media is Professor Sujit Dutt group from Princeton University. So what they did, they took a model porous media again, a microchannel filled with spheres, solid spheres, and then they flowed a viscoelastic fluid through this model porous media. And what they observed, that once the flow rate exceeds a critical value, you can see a chaotic and fluctuating flow behavior due to the appearance of elastic turbulence. Okay, even if you zoom it for one obstacle only, you can see how that turbulent burst is coming, because of the appearance of elastic turbulence. Even in our research group, we have performed numerical simulations, and we have also seen those chaotic fluctuations inside this porous media. Now we asked a very simple question, that what does happen if we continuously increase the flow rate or polymer relaxation time, which is ultimately related to this non-dimensional number, which is called Ojema number. Will this chaotic fluctuation will increase, if we continuously increase the flow strength or polymer relaxation time, or they will reach to a saturation stage? Okay, so what will happen? So that is the simple question we have asked. Okay, and interestingly, what we have found that, so we also carried out numerical simulation for a model porous media, where again we have a micro channel and we place some micro pillars inside it, and then we carried out the simulation at different values of the Eugenberg number. Now you can see that this is Eugen number 0, which is simply for the which is the case of simple Newtonian fluid. You can see a very like order flow state within the flow setup. But as the original number gradually increase, you can see that how the flow becomes distorted. Okay, for instance, at this original number 3, you can see now the definitely the flow becomes chaotic and fluctuating in nature. If you further increase the version number 5 and 10, you can see there will be formation of some preferential paths where through which most of the fluids now passing by. Okay, now if you plot the velocity fluctuations inside this porous media, so at low values of version number, you can see there is no fluctuations. Okay, it is almost zero. But version number 3, you can see that well, we have a lot of fluctuations. Okay, but once we further increase the origin number like 5 and 10, again you can see that the fluctuations are suppressed. Okay, so interestingly, you can see that the velocity fluctuations continuously increase, reaches a maximum, and then again suppressed. So here the intensity of elastic turbulence will be definitely higher, you know but even if you increase the flow strength further, okay, or if you increase the polymer relaxation time by increasing either molecular weight or polymer concentration within your solutions, you can see that the intensity of velocity fluctuation due to elastic turbulence is not increasing, it is getting suppressed. So that's why there's a clear evidence is that there is a non-monotonic variations in the velocity fluctuations, you know inside the porous media. And even we have also calculated the pressure drop across this porous media, and you can see that the pressure drop also gradually increased, reaches a maximum, and then again starts to decrease. Okay, so the pressure drop also clearly shows a non-monotonic variations. Okay, now if you want to capture this pressure drop versus flow strength, so definitely we have that well-known Darcy law, which is well applicable for Newtonian fluid flow through porous media. Now in this case, definitely it will be difficult to use this law to predict this pressure drop because of this non-monotonic behavior. So we have to do something, we have to do some modification within this relationship so that we can accommodate. So we are still working on this topic. On my PhD student, he is actively working, on this problem. So definitely, we'll come up with something which can definitely which will be able to capture this non-monotonic behavior. Okay, but the question is that why there is why we have these non-monotonic variations in velocity fluctuations or pressure drop. So in order to understand that, what we have done, we have again calculated those birefringent strands inside this porous media. So you can see that at version number 1, these strands just start to develop. Okay, but at version number 3, you can see that those strands actually are now fully developed and they also start to fluctuate. Okay, because of the elastic instability, and because of this elastic instability, you know so we have that chaotic fluctuations which was the maximum around this version number 3. But once we increase the flow strength further or the version number further, then what will happen, these strands actually now um, they actually will be locked with the surrounding obstacles. Okay, so they will not be able to now fluctuate. Okay, so you can see that this all these strands now locked with the neighboring obstacles. Okay, so that's the reason why actually the velocity fluctuations is getting suppressed at high oxygen number. Even if you increase the oxygen number further, this locking will be more intense. Okay, so that's why the velocity fluctuation will be suppressed. Okay, so this is like we have explained in terms of this formation of birefringent strands, but definitely we have to do more statistical analysis, you know in order to prove that. Okay, so that we are working. And so this is the overall mechanism that I just discussed. So birefringent strands will be formed and strands will start to oscillate, which will actually generate the elastic turbulence. But if you keep increasing the flow strength, definitely the strands will be locked with the surrounding obstacles. So that's why the fluctuation will be getting suppressed. Okay, as we increase the volume number. Okay, so that's it. I think this is all about the flow of viscoelastic fluid through microporous media. So we are actively working on this topic still, and definitely we will come up with more analysis and results in our future works. Okay, so overall conclusion that I can give in these talks is that The definitely flow of complex fluid very often generates defined instabilities, particularly that elastic instability that I have talked about, which can transit to elastic turbulence regime that can be leveraged to increase the rates of various transport processes like heat transfer or mixing. Okay, now particularly the flow of viscoelastic fluid, you know, through microporous media, what we have seen that there is a non-monotonic variations in the velocity fluctuations and pressure drop, that we have observed. And then the famous Darcy's law actually might not be, as it is, the Darcy's law might not be applicable to predict the pressure drop, for viscoelastic fluid flow through porous media. So you have to do some modification definitely into that law so that it can account that non-monotonic variations. And at the end I can tell you that the complex fluids are everywhere. Okay, and their flow physics definitely is much more complicated and interesting compared to simple Newtonian fluids like water, even under the same operating and flow conditions. So that's why we have to do a lot of research. There are a lot of scopes, there's a lot of scope available for this research area. So if anyone is interested, definitely he or she can pursue. Okay, so with this I'd like to acknowledge to my students, particularly Bilal, my former PhD student who did some of the porous media works, and Anand, who is my current PhD student who is still working actively on this porous media topic. And obviously the funding that I received from IIT Ropar and ANRF to carry out